Hey guys, Dr. Cadell here, and this is the Tools of the Trade Lab. The idea in this experiment is you're going to get introduced to some of the common tools that we use in chemistry. And they're everywhere. We use them all the time, so it's a really good thing. Another thing that we're doing in this experiment is we introduce you guys to the idea of accuracy and precision, and what they mean. We'll talk about that in a minute. There are two parts to this experiment. In the first part, we're going to be measuring the temperature of some water with two different kinds of thermometer, a regular glass thermometer and a digital thermometer. And that gets to another thing that we learn in this experiment, and that is how to read instruments to the correct precision, to the correct number of significant figures. So in the first part of the experiment, what we're going to do is we're going to measure the temperature of some regular tap water with the two kinds of thermometers, glass and digital. Then we're going to put some ice in it and measure the temperature of the ice water. And then we're going to add some salt to that ice water. We should see the temperature go down. We're going to do the same thing, measure the temperature with the glass thermometer and a digital thermometer. And then finally, in the first part, we're going to measure the temperature of some boiling water with both thermometers. And once we get those numbers, we're going to look at our measurements and see which was most accurate. Accurate means how close that measurement is to the real value. Now we know that ice water should be really just about 0 Celsius. And so the thermometer that's closest to 0 Celsius would be the most accurate. Likewise, for boiling water, the thermometer that measures a temperature closest to 100 degrees Celsius would be the most accurate. I'll talk about precision in a little bit in the second part. Now, when we're measuring the temperature with a digital thermometer, any digital instrument, you always record every digit that you see in the display. With the thermometers that we have for this experiment, it's always one place to the right of the decimal, which means if it says 10.0, that 0.0 is important, so you should record 10.0, not just 10. Now, when we read the temperature with a glass thermometer, we get into reading marks like this. So if you look at this picture of a thermometer here, the first thing that's important when you're reading any instrument like this is to figure out how close together the closest marks are to each other. And what you do is you just count between the numbers. So if this is 0 and this is 10, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces, which means that each space, each line is 1 degree Celsius. That is, it's in the ones place. And that's important because this is the rule, guys. Whenever we record a measurement from an instrument that's analog like this, we always record one more place to the right in the number. What does that mean? It means that if these marks are 1 degree apart, we would record that temperature to the 10th place, one to the right of the decimal. And so, for example, this measurement right here, this is 0, 1, 2, 3. The line ends somewhere between 3 degrees Celsius and 4 degrees Celsius. Now you estimate how far it is between those two marks. I said, okay, that's about 80% of the way between 3 and 4, so I call it 3.8 degrees Celsius. The important thing is it's one past the decimal. Everybody understands when they read that number that this 8 was estimated. It could be 3.7, it could be 3.9, but it's close to that. And that's it for the first part. Now, when we look at the second part of the experiment, what we're going to do, guys, is we're going to measure the mass of 10 milliliters of water using different instruments to measure out the 10 milliliters. And ultimately what we do is we compare the mass that we measure, the average mass, because we're going to measure with each instrument 3 times, take the average. We're going to compare the average mass from that instrument to the true value of 10 milliliters of water. And we're going to be able to figure out which of those instruments was the most accurate as well as the most precise. We'll talk about accuracy versus precision in just a minute when we get over there. So the idea is we're going to measure out 10 milliliters of water with first a graduated cylinder 3 times and measure how much its mass is. So a graduated cylinder looks like this, and again, the first thing that we do when we look at that instrument is we see how far apart the closest marks are to each other. So it's going to look something like this. This is 5, 6, 7, 8, 9, 10. Each of these marks is 1 milliliter apart. which means every measurement that we record from this graduated cylinder, we record to the 10th place, one past the decimal. So if this were the top of the meniscus of the water that's in this cylinder, we would record, okay, there's 10, there's 11, there's 12. It's somewhere between 11 and 12. So we estimate how far it is between the 11 and 12. I said, it's a little bit less than half, so I call it 11.4. But again, everybody understands that 4, that's estimated. And the units are milliliters. One other thing about reading this, guys, whenever there's a column of liquid in a cylinder, it always forms a meniscus at the top. And so the way you read that volume is you always find the bottom of that meniscus when it's concave like this. So the way we would read this is we would find the very bottom of this, not up here, but the very bottom of that meniscus, and that's the volume that we measure. The next instrument that we use to measure out 10 milliliters of water so that we can record its mass, measure its mass, is a volumetric pipette. Now, these volumetric pipettes that we use for this experiment measure out 10.00 milliliters. Sig figs are important. When you do it properly, when you measure out liquid with these volumetric pipettes, it's 4 significant figures, 10.00 milliliters to past the decimal. And I'm going to demonstrate how to use these once we get over to the actual experiment portion of this lab. But the important thing here is that there's once more going to be a meniscus, and our goal is that when we pull up the liquid, the water in this case, into the pipette, we need the bottom of the meniscus just touching this line. There's going to be a line in the neck of that volumetric pipette. And if we do that properly, we'll be able to measure out 10.00 milliliters of water. Now, the next instrument that we use to measure out the volume, the 10 milliliters of water that we're going to measure the mass of, is called a burette. And this is what they look like, sort of. Again, first thing that we look at is how far apart the closest marks are to each other. And if we look at this, say this is 1, this is 2, there are 10 marks in between. That means that each of these marks is a 1/10 of a milliliter. And so whenever we record a measurement from the burette, we would record 2 places past the decimal. There's a couple of different things about the burette that we need to be aware of. First is it starts at 0 at the top, not all the way to the top, but there's a mark up here, and it goes down. The reason for that is that burettes are designed to measure volume added to another container. So the way we use a burette, guys, is we read the initial volume. For example, if there's the top of the column of water, I would say, okay, there's 0.5, 0.6, 0.7, 0.8. It's somewhere between 0.7 and 0.8. I estimated 0.78 milliliters. That would be my initial volume. Now in this experiment, our goal is to add 10.00 milliliters with the burette. So what we do is whatever the initial volume is, in your head or on a piece of paper, add 10 to that. So 10.78. What we would do is we'd open up, there's a stopcock down here, open it up and let the water out until it gets down to 10.78 milliliters, close it, and measure the mass. 2 places past the decimal, the burette. All right, so that's what we're going to do in the second part. But now let's talk about why we're doing some of those things. So if we look at these equations over here, in the first part of the experiment, we're going to be figuring out or determining for you which thermometer was most accurate for the ice water and for the boiling water. Accuracy is a measure of how close that measurement is to the true value. So what we're going to do is for each of the thermometers, we're going to take the temperature that we measure, and it's probably won't be right at 0 degrees Celsius. It's going to be something hopefully close to that, and take the difference between what we measure with that thermometer and 0. So when we subtract 0, of course, we get the same number back. These bars here, guys, they mean absolute value. So if this number is less than 0, it could be, we still write positive numbers over there. What we do is we do this for both of the thermometers for the ice water, whichever is closest to 0, has the smallest difference, that's the most accurate. Same thing for boiling water, whichever thermometer is closer to 100 degrees Celsius, that's the most accurate. Now in the second part of the experiment, we're going to compare the mass of 10 milliliters of water that we get for each of the different instruments, the graduated cylinder, the volumetric pipette, and the burette. And because we're going to measure that mass 3 different times, we're going to use the average of each of those 3 for each instrument. And down there, okay, when we do that part, the measure of accuracy is going to be percent error. Percent error is how different, again, it's a measure of how different that measurement is from the true value. To do these calculations, again, please notice the absolute value bar, so even if you get a negative number, just make it positive. And what this says is that the true value, that's the real value of the mass of 10 milliliters of water, minus what you measure, that's your experimental value. That difference divided by the true value times 100 is the percent error. And whichever of those three instruments, the graduated cylinder, the volumetric pipette, or the burette, has the smallest percent error is going to be the most accurate for you. And it's different for different people. It depends upon how careful you are and a lot of different factors. Now, to measure the precision, okay, first of all, precision means how close together the measurements are to each other. So we're taking 3 measurements with each tool. And whichever tool has those 3 measurements the closest to each other is the most precise instrument for you on that day. And the way we measure precision is we first find what's called the deviation. Deviation is just the difference between your measurement for that trial and the average. So this would be trial X. So the first trial, the first measurement, say with the graduated cylinder, would be the mass that you got here, minus the average of the 3 measurements. Absolute value, again, that's a deviation. Because we're going to have 3 deviations for each instrument, we add them up and divide by 3, get our average deviation. Whichever tool has the smallest average deviation would be the most precise for you on that day. So that's what's going on. Why don't we go over here and get started on that experiment. This video is on how to read the density of water as a function of temperature for our tools of the trade lab. So you got a temperature of your water in C10. Now that temperature is going to have one place past the decimal. And the way to read the density of water at that temperature from this table is to first look at the digits to the left of the decimal. So let's say your temperature was 14.7 degrees Celsius. It'll be higher than that, but let's just say. You find the 14, everything to the left of the decimal, in the left-hand column of this table. So there's my 14 in green right here. Then we find the digit to the right of the decimal, rather, in this case the 0.7 in the top row. And just where that column under the 0.7, or whatever your last decimal is, and the row, my 14, where those two intersect, that number is the density of water at your temperature. The units are grams per milliliter, and every one of those numbers is significant. So there are 6 significant figures, and you should write them all down. And that's really all there is to it. All right, guys, so this is the first part of Tools of the Trade experiment. So all we do is we're going to measure the temperature of, first, some tap water. So I have some regular old tap water in here. Take a glass thermometer, place it in here. Now a couple things about using the glass thermometer. If you can, you want to try to avoid touching the bottom or the sides with the red tip. Submerge it, about halfway. Give it a chance to equilibrate, and then read that temperature. Remember, one place past the decimal. That would be your A1. Now we're going to do the same thing with the digital thermometer. A couple things about the digital thermometer. First, that's a cover. Take it off. Next, there's 2 buttons. One turns it on and off, so turn it on. It's real important when you finish with this, you turn it off, because these are run with batteries, and if you leave it on, of course, the battery dies. Next, there's a switch that goes between degrees Fahrenheit and degrees Celsius. We always use degrees Celsius in here, so make sure it's on the degrees Celsius. And then with the digital thermometer, you want to, if you can, you want to try avoid touching this metal part when you're reading a temperature, because the heat from your hands could alter the temperature that it reads. So hold it on the plastic part up here. Put the tip about halfway down. Again, try not to touch the bottom or the sides. And this is digital, so we record every digit that's on there, which will also be one place to the right of the decimal. And that's going to be your A2. Once we get those two, we're going to take and we're going to put some ice in. I'm just going to scoop some ice. So just like we did with regular tap water, glass thermometer, record that temperature. This should be somewhere around 0, probably won't be exactly right at 0.0, but record whatever we read, one place past the decimal, and that's going to be A3. Likewise, with the digital thermometer, put it in there, hold it on the plastic part, give it a minute to equilibrate. One place past the decimal, that's going to be your A4. Once we get those, we're going to add a little bit of salt. Now, what salt does is it lowers the freezing point of the ice, and which means that we expect it to be a little bit colder. So we don't have to measure this out carefully. There's a plastic spoon here. Just take a scoop, dump it in. We can even put a little more if we wanted to. Always put the lid back on everything. And we need to stir it up. We can use either your glass stirring rod from your locker, or if you're careful like this, you can use the thermometer. It probably won't all dissolve. That's okay, as long as we get as much as we can dissolved. And then, same thing. Record that temperature, one place past the decimal. That's going to be A5. Digital thermometer, holding on the plastic portion in the middle. Give it a chance to come down there. And record that. That's going to be your A6. Now, real quick, with the glass thermometer, it has negative readings on here, so anything below 0, it goes down by 1 degree Celsius and it's negative. This one, the digital, it has a negative sign in front when it's negative. Then the last thing for this part is the boiling water we have over here. So once more, we'll take the glass thermometer. Again, this part, it's really important, guys, we don't touch the bottom, because that hot plate is a lot hotter than the actual water is, and that'll give us a false reading. So put it about halfway down, give it a chance to equilibrate. Read that. Should be pretty close to 100, probably won't be exactly 100.0. Give it a chance, record that one place to the right of the decimal. That's your A7. And then same thing with the digital thermometer. Again, hold it on the plastic portion, don't touch the bottom. Give it a chance to come to temperature. Record that temperature, of course, one place past the decimal, degrees Celsius. That's A8. And we're finished with the first part of the experiment. Make sure we turn off the thermometer. And we can turn off our water now too. By the way, whenever you're moving something that's hot like this, we have beaker tongs right here. You don't want to pick it up with your hands, that's for sure. Just take this off and set it over here on a piece of wire box. All right, so now the second portion, guys, second part of the experiment. All we're going to do is we're going to measure out the mass of 10 milliliters of water, and the difference is we measure the volume with 3 different instruments. So to do that, we're going to take an empty 150 milliliter beaker, and we're going to use the balance here, which we have not used before maybe. So the balance, we don't care how much the beaker weighs, so we're going to use the tare function on the balance. To do that, place the empty beaker on the balance, close all the doors, and press the button on the front, and it should read 0 all the way across with the empty beaker on there. So it's subtracting the mass of the beaker for us. Digital, so that means we record every digit that's there. These balances are 3 places past the decimal, to the right of the decimal, and the units are little g for grams. So we take this out. I already have 10 milliliters water measured in this graduated cylinder. The bottom of my meniscus is touching the top of the 10 line. Pour it in. Place it back on the balance. Close the door. Record that number, 3 places past the decimal, little g for grams. That's going to be my B1. And all these numbers should be really close to 10, a little bit under 10 actually. And then what I do is, with the water in the beaker, I tear out the balance. So now it says 0 with the beaker and the water in there. Take that out, add 10 more milliliters with the graduated cylinder. That'll be my B2. Do that again, that's my B3. Now we're ready for the volumetric pipette. So after the 3rd measurement with the graduated cylinder, tear out the balance. It says 0 with the beaker and the water on there. Take it out. Now, the volumetric pipette. This is the volumetric pipette, and all volumetric pipettes have a line somewhere on the neck right here, a thin line, and that's our 10.00 milliliter mark. So what I do is I take a pipette bulb and pull up water, some deionized water. I'm going to use the wash bottle here. The way I do that is I squeeze the bulb. Now this bulb is an inverted cone inside of it. It doesn't lock onto the volumetric pipette. You just kind of have to move it around and find where it seals best. So I squeeze it, keep it squeezed, place it on there, move it around. Now, one trick that's really important with the volumetric pipette is before you start, you want to make sure that the inside of the pipette bulb is dry, the top of the pipette is dry, and your left forefinger is dry. If any one of those are wet, it makes this basically impossible to do accurately. So I'll show you why in just a sec. Squeeze the bulb, keep it squeezed, place it on top of the pipette, and lift the pipette off a little bit from the bottom and start pulling up the water. And I'm going to bring it up above that mark somewhere. Now with it up there, we want to make sure we don't get any water up in the bulb because then everything gets hard. Take off the bulb real quick, and I put my left forefinger on top of the pipette. Now this part is why it's important for all that stuff to be dry, because what we do now is I'm going to look at that line, and I'm going to look at the meniscus. I'm going to release a little bit of pressure with my finger and twist the pipette. And I can get a drop at a time to come out. And I'm going to keep doing that until the bottom of that meniscus just touches the top of that line. Well, if anything's wet in here, it forms a seal at the top of the pipette, and it's basically impossible to do this. So I have it set there. I put the pressure back down. I take my tared beaker with the water in it, and I let gravity pull the water out. Now, what we don't want to do, guys, is we don't want to push the water out with the bulb. I'll show you why in just a second here. So once the water stops coming out just from gravity, we touch the tip of the pipette to the side of the beaker. Now there's a little bit of water left in there. It's supposed to be in there. This pipette is calibrated so that the way I just did it, I added 10.00 milliliters. If I had pushed the rest of this water out with a bulb, then it's more than 10 mils, and we don't know how much. So anyway, put it back on the balance, close the door. Record that measurement 3 places past the decimal, little g for grams. That's going to be my B4. Then I'm going to tear it out with the beaker and the water on there so it says 0. Do the same thing 2 more times. That's B5 and B6. After that, I'm ready for the buret, which is right here. So after my last volumetric pipette measurement, I tear out the balance with the beaker and the water on there. Notice I never dumped the water out until the very end. Take it over here. Now, with the buret, I've already put some deionized water in here, but there's still a couple things I have to do. The first thing is there's going to be some air in the tip of this buret right here. And I need to get that air out. So I just take some waste beaker and I open up the stopcock. This is the stopcock right here in the buret. It's closed when it's perpendicular to the buret. It's open when it's parallel. So I open it up, flick the tip, and a few air bubbles came out. And I want to make sure that the level of my water is below the 0 mark somewhere. Doesn't matter. So now I have the air out. I'm ready to go. I read my initial volume reading 2 places past the decimal. In my mind, I add 10 to that, see where that is. And then put my tared beaker with the water still in it underneath it. Open this up. Now once the level gets close to where I want to stop, I'm going to close the stopcock, and then I can go really carefully. So now if I twist this stopcock 180 degrees, just a little bit comes out, and I can control that really quite well. The faster I twist the stopcock, the less comes out and the more precise I can be. So once I get down to right where I want to be, I'm going to take this out, put it on the tared balance, close that door. That's going to be my B7. Once I record that 3 places past the decimal, little g for grams, tear out the balance, take it out, add 10 more mils, probably have to add a little bit back into the buret, that's fine. Do that 2 more times, that's B8 and B9. Now we're not quite done. The last thing we have to do is we're going to have about 90 milliliters of water in the beaker at that point. we need to measure the temperature. So what we do is we take the digital thermometer, turn it on, record this temperature. 1 place past the decimal, degrees Celsius, that's going to be B10. Now the reason, guys, that we need that is that the density of water depends upon the temperature. As the temperature changes, the density changes. And we're going to look up the density of water at this temperature and use that density to calculate in the lab report, which I take you through, what the true value is for the mass of that 10 milliliters of water. That's what we're going to use to find the percent error and the precision of each of these instruments. So that's the last part of this experiment, and that's all there is to it.